Okay. So apologize for any inconvenience. I didn't invite you to the Zoom. So let me start my section of environmental engineering introduction class. So this is the first class, and April 13th, this is water treatment class today. And the coming Thursday, we are going to water treatment again to finish up and wind up. And desalination process also will be discussed. And the next week, we are going to have a midterm period. We don't have a class of these and other classes as well. And 2 weeks from today, on Tuesday, which is 27th April, so we are discussing, or I will introduce you alternative technology. So specifically ecological engineering types of water treatment as well as wastewater treatment process for both the small community and even metropolitan city. We can think about and take those technology for treating water and providing safe drinking water to a metropolitan city as well. And 29th April, so the Thursday, which is Thursday, the 2 weeks from this coming Thursday. So then I didn't decide yet, but I will let you know in a few days. And then May 4th, so we are going to have a quiz and examination based on our discussion. So we have in total 5 different classes under my the lecturing. Okay, so welcome to my section of introduction to environmental engineering. So we have water. So we need water. So then I'm not sure you drink tap water without any further treatment. But we have the issue of water qualities. But as well as we have aesthetic the issues. So even if water treatment plant that provide you very clean and safe drinking water, but not many person drink tap water without any further. So they prefer to use a personal purifier, which is 정수기 in Korean, at home to guarantee as much as possible to drink safe drinking water. So there are some issues of water qualities, but as well as I mentioned earlier, so we have a issue of aesthetic or trusty issues. So the other countries, for example, and US and European countries, they drink tap water without any further. So mostly they drink, many times been looking at those situations, but in Korea, only 7% drink tap water without any further treatment processes. So even right now, so recently, the potable water, 생수, potable water is very popular in Korea. Somebody order those water to drink at home even. And so the tap water, our 수돗물, they've been using for other purposes, and the laundry, the washing, and the cooking, and other the purposes as well. So so we are discussing those issues as well. But if you have any questions, if you have any comment, also you may be sometimes a water engineer in your future career to provide the water to the citizens. So sometimes you have an opportunity to convince citizens to use this tap water without further treatment. So water quality is already guaranteed right now by law and by regulations. Okay, so what contaminant do we have? We generally use river water, lake water, even the seawater to make a safe drinking water, safe potable water. So those water resources, so including river, lake, groundwater, and the seawater, they have a contamination in it. then we would like to remove, we would like to separate those contamination out of the water to make a safe and clean water. So what kind of contamination do you think we have in groundwater, river water, lake, and seawater? And then so against those contaminations, so we would like to select the technology and process to remove, sometimes separate out of water contamination such as the particle, colloid, the virus, and the bacteria, and organic matters, ions, so some others as well. So that's the everything, pretty much everything. So if you understand the contamination we have in our source water, and then you can design a technology or processes to tackle with the contamination. That's the pretty much almost to this the class, especially my sections. Okay. So which water do you think, this is just a common sense, which water is cleanest the sources out of river, lake, groundwater, and seawater? What do you think? Which one is cleanest? Is cleaner than the other? What do you think? Seawater? Why do you think seawater is clean? Why? So you may say, okay, you may use chatting, but you may tell groundwater, river water. Some of you mentioned groundwater. Why do you think groundwater? It is groundwater actually. So why do you think groundwater is cleaner than the other? This is very important. So this is engineering class, technology-based class. I agree. So we need the knowledge to design the water treatment plan, facilities, of course. But so common senses are also important. If you go to Vietnam, if you go to so other countries like Vietnam and Cambodia, so they suffer from the dirty water. Even if you go to African countries to provide the children with safe drinking water, so that then you may not have any instrument to measure water qualities, but so you have a engineering sense and common sense as well. So groundwater is the cleanest, so you make a well to get the water, to provide water, but you have to understand what kind of contamination still are contaminated with those groundwater. The Park Jung-in mentioned under groundwater can be easily contaminated with pollutant from the human. So groundwater is not clean, do you think? So it may be contaminated by human activity, especially from the farming, fertilizer, and many others as well. But groundwater, actually water is the place between soil, right? Soil has capability to purify, because the soil has the surface, the higher surface water. On the surface water, surface area around the soil, so contamination actually attached. So attached contamination out of water make water, those corresponding water, cleaner than before. So with other conditions being the same, groundwater can be first priority for us to take, to drink without any contamination sometimes, without any further treatment sometimes. But depending on situation, I agree. If you go to Vietnam, if you go to the Cambodia, if you go to Bangladesh, so groundwater generally are contaminated with arsenic. So you don't want to drink groundwater when you're visiting Vietnam, Cambodia, and Bangladesh especially. Taiwan as well. Taiwan, most of Taiwan groundwater contaminated with arsenic. Arsenic is in Korean. You know arsenic, right? You know arsenic. Arsenic is biso in Korean. So symbol is AS. AS is the toxic material long time ago in Lee Dynasty. So they tried to use this arsenic, bisang, to kill king. So they add arsenic, small amount, not noticed. So in the food for king, so a king take this arsenic, small, but even if its amount is small, but accumulated inside the body of the king, that come up with some kind of a death. So if you look at the drama of Hejun, so sometimes the doctor use arsenic to cure patient for some reasons, but actually arsenic is very toxic, the present at the groundwater. But generally speaking, groundwater is cleaner than the other one. The seawater is the clean as well. Sea is generally clean. So sea area is huge. Okay, so contamination, of course, but generally dilute the other seawater. How about the river? For example, to take a sample from Nakdong River. Do you think it's clean compared to water in from the sea, from the groundwater, from the lake of Palta? No. Okay, thank you. So then the river is worse. But so the other countries are absolutely different situations. But in Korea, river is the worst case, I believe. Especially Nakdong is the worst situations. Nakdong River. So we have other river. For example, Somjin River in Jeolla province near the Hadong. Those water quality is much better than ones of Nakdong River. How about the Han River? How about the Gum River? How about the Yeongsan River? Which one is best? Which one is best in water qualities? They're all the same, I believe. So Nakdong is the worst. Nakdong is the worst. That's why we have to be very, very careful to use this Nakdong River for our drinking water source. But Han River, Hangang, Yeongsangang, Gumgang, pretty much similar in water qualities. So we take a sample from the river to make our potable water, tap water, which is 수돗물. Then, first we have to understand what kind of contamination we have. And then, depending on contaminations, depending on pollutant, then we can design certain processes to remove out of water to provide safe drinking water to citizens. So here in Ulsan and Busan and Gyeongsang province, so we have a tap water treated out of Nakdong River. Okay, Nakdong River. So you are confident in water quality with our tap water. Is that true? Are you confident? Do you have a confidence in water quality for your tap water? So probably not. Probably not. So that's why we study these types of that. Okay. Okay. So here is the candidate of particle. The bigger size and smaller size. So we have a particle and colloid. Particle and colloid. So you know that. The particles such as the sand, small particle, fine particles, super fine particle like 미세먼지, and you have a colloid as well in our source water. So for example, we got the coffee. So if you ground the coffee and to make the morning coffee, so coffee, there is a colloid. What could be the big difference in definition between the particle and colloid? What do you think? Particle and colloid. What make a big difference between two? The particle, such as sand, colloid, such as coffee, such as clay. What could be difference? In engineering definition, they have a different size. And the phenomena, if you put the particle, any particle in water, what happened? If you put the colloid in your water, what happened? In different way, you can describe. So particle, if you put the particle in your water in Nakdong River, in the sea waters and the clean water, the particle slowly or relatively fast and settle down toward the bottom. How about the colloid? They never settled down. They never moved toward the bottom because they are influenced by gravity, but they also have the power of buoyancy. So with water, so they have they are affected by gravity to move downward, but colloid as well. So have some kind of water, some forces to upward. So those are the forces and the balanced, such as clay, such as coffee. So the colloid contamination in water, so they stay where they are. So they never settle down. So this means with the colloid contaminated in our water, it is relatively difficult to remove this one through settlement. If you have a particle of sand, if you have a particle of gravel, much bigger than sand, so relatively easy to remove a particle. By what? Take a time to wait until those particles settle down toward the bottom, and then we take upper side of water to drink it. It seems clean, it seems safe, but colloid is different. If you put the coffee, so coffee colloid never settled down, right? So not removed at all. So 4 hours, 4 days, so they still remain. Some colloid actually to be settled down, but in a small amount. So that's the tactic. So how we select appropriate process to remove this colloid. Why colloid can be and maybe removed out of water. That's what we are going to discuss. And organic matter. So inside, which one are bigger than the other between colloid and organic matter, do you think? They're probably colloid. Okay, organic matter has, yes, thank you. So colloid may be the bigger than organic matter. So there are organic matter has a higher, very high molecular weight, 분자량, molecular weight. So size-wise, some organic matters may be bigger than colloid, but generally, generally colloid is bigger than organic matter. So I believe you studied the organic chemistry. How about the iron? The thirdly, the iron, nitrate, sulfate, and the phosphate. So there are the toxic ion like arsenic. Arsenic already mentioned, the BSO, especially in groundwater. Through the Mekong River, so from China to the Cambodia, through the Myanmar and the Cambodia and the Vietnam. So there is the Mekong River. Mekong River and the connected groundwater are generally contaminated with arsenic. Arsenic in groundwater has a different valency. Sometimes octavalent, sometimes trivalent, 3가, 5가. So we are going to discuss that in a different class, but arsenic are ions as well. Ions as well. So and the microorganisms including virus and bacteria. Virus and bacteria. The bacteria is bigger than virus, right? And the virus is very weak. So then easy to be killed by chlorine. So bacteria sometimes resist to that. So protozoa. So virus, bacteria, we have a protozoa as well in our water. Protozoa is very, very much the powerful, enough to resist to certain attack by chemical. The virus is weakest. So bacteria is something middle between 3, and the protozoa is very, very strong to survive under harsh conditions with disinfections. So we have these four contaminations. Okay. So please look at the size. Please look at the size. Okay. Okay. So please look at this size. So particle like sand is about 1,000 micrometer, 100 micrometer, 10 micrometer with bacteria and cyst. 1 micron the bacteria. So E. coli in your intestine, so in the feces and even in soil, we have a lot of bacteria, microorganisms in it. The size is approximately micron size. So bigger than the other. Okay, and then we have a colloid, the coffee and clay. We have the colloid in water as well. And then the virus size is a little bit smaller than colloid and bacteria, but still big compared to the organic matter. So about the 0.1 micron. So dissolved organic matters, the big range, smaller molecular weight, higher molecular weight, a size of organic matter. So ions about this range, nanometer size, 10 to the minus 9 meter. Okay, so that's the nanometer size. So if pure water only contaminated with the sand, what kind of a treatment process do you want to use? If pure water is only contaminated with the sand, which is particle, what kind of process we can use? Okay, settlement and filter. What kind of filter do you think, Kim Yong-gi? What kind of filter do you have in your mind to remove sand? Okay, filter is fine. Filter is absolutely fine. Okay, but what kind of filter do you have in your mind? Membrane filter. Okay. Okay, I will get to that. We are going to get to that. Okay, thank you very much. Okay, settlement sometimes enough. So we are engineer. We are not sometimes not a scientist. With water, we probably want to be engineer. So to remove sand. So we don't want to spend the big money to remove sand, because sand is easy to remove, right? To remove, very easy to. So if you go to the African countries for children to provide them the safe drinking water, but so you recognize those water from groundwater or any other water resources. If their water are contaminated with only sand, so we can wait. So we can wait and take upper side of water, so enough to clean enough to be used, right? Okay, and then so there are different situations. So your water is a contaminated bacteria. What happened? Only with bacteria. So this is not the expertise types of questions. So this is a common sense. So we are common sense. We have from the public, from our textbook, so from high school, from our parents. So we've been learning those common sense. So we have a bacteria. How we remove bacteria? Disinfection is okay. So then if you go to African countries, so you know those water contaminated with the bacteria. What kind of disinfection can you use in place without any treatment, other options? Okay, Lee Dong-hyuk mentioned 항생제. 항생제 is different from disinfection. Disinfection in Korea, 소독. So 항생제, so we take those pill into our intestine to resist the attack from the bacteria, from the microorganisms. So HCl, we know the breacher, okay, oxy types of that. So we use this one for our bathroom, toilet. So absolutely right, HCl is one of the strong disinfections. So you put the HCl into water. What do you think? It's okay? And then you can drink it. So a lot of different things are happening in this water treatment. So think about. So this is very challenging process. So right now, somebody make a drinking water to supply us with the safe and drinking water, and then we drink it or we buy potable water. It is okay. It is okay. But we are engineers. Sometimes we have to have other countries as well, who and which are suffering from the dirty water, such in the African countries and other Asian countries, other countries as well, even in domestic 국내, and then we can find alternative way without chemical, without pill, without expensive process. Absolutely right. We can boil the water. The boil and hot temperature kill bacteria. Hot temperature bacteria. So please look at this bacteria. Bacteria size range from 0.5 micron to about 20 and 30 micron. So huge range. So the bacteria has different in size. If you select one bacteria from this side and the other side, put in the water, what happened? They settle toward the bottom. They settle. Do you think? What do you think? So if they are settled down, we don't have to use disinfection, boiling, because they can easily removed out of water, right? So we are engineer, so we have to select efficient and effective technology. So bacteria is big enough to be settled down to the bottom, and we don't have to use any other processes. But if you select a very small bacteria, like a colloid, like a coffee, like a clay, they floated forever. They never settle down. They never settle down, right? So we have to do something. But something between, there are specific and magic number, the beyond and below specific number. So in water, buoyancy force. So this is fluid mechanics, buoyancy force and set gravitational force equal to each other to make a bacteria float the forever. What could be the certain specific number? This number was found by the famous physicist Albert Einstein a long time ago with his paper, buoyancy and Brownian motion. You heard about it, right? Brownian motion by physicist Albert Einstein. He got the Nobel the physicist prize a long time ago from his three different paper. But with the buoyancy process, there are specific number found by Albert Einstein. What is it? Do you remember, or do you know which is specific number? That is 0.45 micron. 0.45 micrometer. So then if you do the scientific engineering experiment, you quite often have to use a filter to remove a particle out of your sample. So then you have to use a filter with a pore size of 0.45. Why we have to use this 0.45 micrometer? We may use 0.3 micrometer, 0.5 micrometer, 0.6, why not? 0.2, why not? Why only? Most people been using this 0.45 micrometer. Some kind of promise, some kind of agreement to be used with this size. Why? From Einstein. So here they discover this size is kind of a boundary. So depending on situations, so sometimes not, sometimes yes. 0.45 is a magic number of 0.55 within with the particle, with the colloid, with the bacteria at which surrounding forces can be balanced each other to make those contamination to be floated forever. So you know what I'm saying? So if we can measure bacteria in size, our bacteria size is higher than 2 micron, for example, 3 micron. So then we can wait, right? We can wait until they are settled down. But if you measure, they come up with a size of 0.1 micron with our bacteria, then we have to do something because they are not easy to be removed through settlement. Okay, you understand? So this is engineering class. So this is not a chemistry and physics class. So depending on situation, depending on environment, depending on water qualities, depending on chemistry. So everything affect those phenomena behind the bacteria, or even shape of bacteria. Rather types of bacteria so float more preferentially, okay, than the circular one. So a lot of different the facts we have to consider. But generally, so please, so you don't have to memorize, but you probably want to memorize this size. This number, 0.45 micron, is from actually the famous physicist Albert Einstein, from his the paper of Brownian motions. And then you have a colloid. We don't want to wait so they resist to be settled down to the bottom. Then we have to use something. So with a colloid, so you might not aware of the appropriate technology to remove this colloid. But are there someone to tell appropriate technology to remove this colloid out of water? If you have a coffee right now, so coffee, the color, which is black, never disappear because the colloid is there, right? You put the coffee there, and tomorrow you find the same color, approximately the same color, almost the same color, because the colloid of coffee is still there, have not been removed through a settlement. What kind of process can be used to remove this colloid out of your coffee? If you would like to make a clean and a transparent water by remove the coffee colloid out of your coffee, what kind of process can you use, do you think? Okay, coagulation, you know that we can use coagulations, okay? But this is not common sense, right? if you encounter the citizens and your parents, they don't know about the coagulation. Right? Is there other the processes or the common? So if you encounter these types of event and situation in African countries, with the water having the colloid in it, then you don't have any coagulation process. You don't have any microcell, microfiltration and membrane. How you actually make those water clean as possible? If you are distillation, yes, distillation is absolutely right. But distillation make a very small amount of water. Okay. So from the sunlight, from the heat, we can make distilled water step by step. Probably not enough to be used by African children. What kind of other processes? So once again, I'd like to tell you with the meaning, we are engineer. So if we are doctors, for example, so to help children in Africa, in Asian countries, or in Korean countries during war, long time ago, to help children that suffer from disease. But think about, we don't have a medicine. If we don't have a medicine as the doctor, how we actually help children suffer from disease? So do you think they are still doctor? So if you are an engineer and go to African countries and Korean the village during war, long time ago, in Asian countries, so we find very dirty water, but there is no other options for children to drink, and then we have to provide those water to the children, okay? And we know at least those water contaminated with colloid, colloid. Then we provide those water without any further treatment? No. The children is very weak. Immunization system, immune system is not that much strong to be enough to resist those related other disease and microorganisms as well. Then we have to do something. We have to do something. We must do something. So what kind of a process do you think as an engineer? Without any coagulant, without any membrane, without any other the chemicals. Okay, boiling. Okay, so that's good. Thank you, actually. So boiling is possible. But boiling remove all the colloid, do you think? Think about, so we have to think about those. And the Kim Yong-gi mentions small sand. Small sand as a filter, right? Small sand as a filter. Absolutely right. Okay, that's very good. That's very good. And ultraviolet. Okay, let me see. Ultraviolet is disinfections. 소독, disinfection. Ultraviolet somehow killed bacteria and virus as well, but not totally, cannot remove totally colloid. So disinfections, UV light works to some extent, but cannot remove colloid totally. Right? The colloid is a very difficult one to be removed. But engineer to do something. So please think about, okay, not today, not only today, for your other, okay, for example, quiz and examinations, I might provide information about the colloid, and then you may design your own the processes to remove this colloid. Electricity, what do you mean by the electricity? Okay, that's very good. Okay, so electricity, we can use it even in an isolated village. Okay, that's good. Okay, but you have to understand what kind of mechanisms. You have to explain to me or to citizens and the villagers how you remove the colloid out of electricity, right? Why do we care about too much about the colloid? Because the colloid size is confused with the size of a virus. Once we contaminated with the virus for our water, so we may drink virus, and then we may be contaminated to be sick. Okay, so that's the very important issue to be treated with this one. Okay. So we are get to that. So thank you very much for your participation. Okay, UV and electricity, the filter and the sand, everything is absolutely fine, but not totally. So some advantage and the limitation as well. How about the organic matter? How about the organic matters? Some organic matters are not toxic at all. Like tea, like coffee, and everything is organic. Okay, please look at this tea. So I can drink. This is organic matter. Organic matter is not toxic sometimes. So we can drink this one. But organic matter sometimes toxic, but not that often. But if we use disinfectants in our water to kill virus and bacteria, our chemical of disinfection can be reacted with organic matter to produce another byproduct, okay, which may be toxic, which may be carcinogen material, and then we have to care. We have to care about those. Wow. You understand the situation. Okay. And then we have ions. So some ions is okay. The sulfate and the phosphate is okay. And the bicarbonate is okay. So we have water in a relatively high concentration is fine. The sulfate, once again, a phosphate, and a bicarbonate, and everything is fine. But so if you have in your water a nitrate, for example, nitrate, NO3 minus, NO3 minus, and ammonia, ammonium ion, NH4 plus. H4 plus, which is ammonia, and nitrate, NO3 minus, NO3, okay, NO3 minus. Okay, why? These two are generally contaminated in our groundwater, which is toxic. So which one is more toxic than the other, do you think? Which one is more toxic than the other, ammonia or nitrate? What do you think? Ammonia is toxic or nitrate is toxic? Both are toxic, but which one is worse, do you think? And why? So knowledge is everywhere, and you can get the knowledge from internet. But so please understand that today's class is more like an introduction. So to understand that, to be familiar with the contaminations and water treatment and water and some kind of physics, some chemistry as well. Nitrate. Do you think Junho, Cha Junho, think nitrates is worse than, more toxic than ammonia? So other opinion? Or nitrate because of oxygen. That's great. Okay, I'm not sure. So I didn't think that way, but it's very good. Jung Jin Hee, very good. Okay. Other opinion? Someone has the opinion that ammonia is more toxic than nitrate. So to Jung Jin Hee. Okay, so oxygen containing chemical may be toxic. So I agree. So to my knowledge, I'm not a chemist, but I agree. But we use the oxygen for our metabolism, right? So oxygen can be toxic, but not every time, every cases. So actually, ammonia is more toxic than nitrate. Ammonia is more toxic. So ammonia, with the concentration of generally 1 ppm, is a toxic, the boundary. The beyond 1 ppm, 1 milligram per liter ammonia. So we have to conserve. We have to remove ammonia out of that to be used for our drinking water. So with the water having feces. So ammonia, if ammonia contaminated the higher than 1 ppm and other, the fish can be blind from disease because of a toxic of ammonia. So ammonia is that much toxic. How about the nitrate? Nitrate, the water, the quality, the regulation is about 10 ppm. Okay, so not exactly 10 times, but the relatively amount of those, the 10 ppm is the boundary between safe, and toxic with nitrate. Nitrate is 질산, 질산성, 질소. Nitrate is 질산성, 질소. Ammonia is ammonia성, 질소. Okay. So if your water contaminated with ammonia, for example, if your water contaminated with this level, right? With this level, ions contaminated with ammonia, what kind of water is it? For example, what kind of water can be contaminated with ammonia? Around us, please look at ammonia contaminated water. What is it? What could be? Example. Please. Okay. Okay. 생활 폐수? Okay, thank you. Absolutely right. 자준호, thank you. Aquarium. What is it? Aquarium. Sorry for that. So I'm always bad at. Okay, urine. Aquarium. Okay. Aquarium water. So having fishes, they emit their urine into the water, and those water contaminated with ammonia. Absolutely right. Okay. And urine as well. So urine has ammonia. So I may ask you, the urine has ammonia? To Yonggi, Kim Yonggi, do you think? What happened? What happened to urine? Urine does not have ammonia. But okay, Kim Yonggi was right. Okay, Kim Yonggi was no. You don't have to sorry. So I'm really thank you. So your urine does not have ammonia, but urea, right? Urea, which is organic. But urea hydrolyzed to be transformed into ammonia. Okay, you are absolutely right, Kim Yonggi. Okay, thank you. You are excellent. So our urine does not have ammonia, but with after excretions, those one contaminated or reaction with the water, vapor and water, that's urea can be transformed into ammonia. So that's why our urine has ammonia. Absolutely right. Sweat has ammonia. So I'm not sure. Okay, this is a very good point, Jeongjin Hee. Very good point. So our sweat has a lot of salt, but ammonia probably. I'm not sure. So I look at that. So probably sweat. So those are the things. So then you have an aquarium, like Park Jung-in. Then aquarium water may be contaminated with the fish, contaminated with the ammonia. So the fish can be sick out of urine, out of ammonia, because ammonia is very toxic. So then we have to clean those ammonia, right? Okay, from farm. Yes, that's true. And then how we actually remove ammonia? How we remove ammonia? If the water and contaminated with the sand, and then relatively easy, right? We already know settlement. And the bacteria, probably we have to use other processes like sand filtrations. So we collected the sand and filter through the sand to remove bacteria. And the colloid, then we'll get to that in a second, in few days, in few classes. And salt. So then ammonia is the most difficult things to remove it. So this is hot. This is very hot area in water treatment and even wastewater treatment processes to remove ammonia. Okay. Virtually, virtually it is almost impossible to remove. Other contaminations like sand, bacteria, colloid, even organic matter, we can remove it. We can remove it. So someone in the part of this class mentioned the membrane process. Membrane is a filter. Membrane is a filter. So we've been using membrane for our purifier, 정수기 at home. So we can use membrane to remove sand. We can use membrane to remove bacteria, cyst, virus, and colloid, everything, even organic matter. But even if we use the membrane process from your purifier, 정수기, we cannot remove ammonia. We can remove nitrate. We can remove nitrate by membrane, but we cannot remove ammonia. So very hot issue right now. Okay, someone mentioned zeolite. Okay, that's good. So we can get to that. Hopefully, I'm not sure we have enough time. The zeolite, the nanoparticle to processes the reaction with ammonia to convert those other one to be observed onto the surface of a nanoparticle. Absolutely good. That's very good. Okay, so I'm not a nanoparticle person, but zeolite and other nanoparticle technology, absolutely excellent process to be used. But ammonia, I'm not sure. Okay, so we are get to that. So even desalination process, 해수, 담수화, desalination process, ammonia is not easy to remove. So please, if you go to anywhere to treat the treatment processes, including desalination, including NGO activities, if your water contaminated with ammonia, and try to find other sources. Okay, ammonia is that much hard, almost impossible to remove those out of your water. Okay, dilution. Okay, but dilution. So dilution requires us to enough water to dilute ammonia, right? Okay, that's good. That's good, but water is water. We need water enough to be used for dilution. So from farm, okay, ammonia from farm. Our fertilizer, okay, 퇴비, 액비, fertilizer have ammonia in it. That's excellent. 자주노, excellent. So then our farm contaminate our groundwater. So that's why. Okay. So let me give you one example. So we would like to use our urine, 오줌, urine for our fertilizer. What could be best option before being utilized for our farm with the urine? So urine has urea, okay, 요소, urea, 요소. But so it is very difficult to keep those urea with the urine because the urine exposed to atmosphere and water. Urea organic transform suddenly into ammonia, right? So ammonia is good, still good for our plants, vegetable in the farm, but may be toxic and may contaminate our groundwater, right? The best option could be with our urine. Inside the urine, and we have urea. Urea can be easily transformed to nitrate, ammonia. And then if there is one option and the process is to transform ammonia to nitrate. Okay, how about it? If you have a certain processes and chemical processes, the physical processes, whatever processes that can transform ammonia to nitrate, number one options, what could be? Toxic wise, nitrate is less toxic than ammonia. That's the first advantage for us to get. The second option, we will get to that in a few classes, but nitrate is much more easier to be removed from water than ammonia. Ammonia is toughest one. Okay, very difficult one, almost impossible sometimes. I already mentioned. So ammonia is that much. So first option, toxicity. So ammonia is more toxic. The second option, treatment option, priority. Nitrate is much easier to remove from water. Okay. So already you mentioned, so ammonia can be oxidized, right? Ammonia can be oxidized to nitrate because please look at the chemical formula. Ammonia is NH4, nitrate NO3. So nitrate is the more oxidizing the state. So we can, if we have a certain process to oxidize ammonia to nitrate, is the best scenario for us. So a nitrate contaminated groundwater is still contaminated, but less toxic level, right? So this is very important, I believe. Okay, any questions? I had better stop today. So we have a lot of contaminations from the particle to colloid to the virus and organic matters and to ions. Okay, all the range of this one. So from time to time, so we don't have to invest the money to design any processes with the contamination certain because they disappear automatically. But we have to concern the certain contaminations because they are very resistant to any processes. For example, ammonia. And there are another one as well. I will introduce those to you in coming classes, but ammonia is one of those. But we can use chemistry, we can use physical, the processes, the movement. So that's why we study, that's why we do research with those issues. Okay, questions? Any questions? No? Okay, thank you for your participation and active reply to my questions. And thank you for your attention and see you Thursday. Okay, thank you very much. Thank you.